talk on XArrays. Please welcome Howard.
So good morning everybody. I'll try not to keep you too long from your lunch. My name is Robin Wilson and I'm going to talk about XArray. Now I should first of all point out that I'm not a developer of XArray. I've submitted a few minor pull requests but nothing more than that. I'm just a happy user, and a happy user of a module that I think is underknown and underappreciated in the Python world. But I'm actually going to start my talk with something that's quite related to the previous talk here about air pollution. My previous area of work was in satellite imagery, and I had a lot of satellite maps of air pollution. So rather than the indoor personalised measurements of carrying around the sensor with you that we were talking about in the previous talk, this is looking down from a satellite, looking at basically the haziness of the atmosphere and getting a measurement of the air pollution. And I was also looking at particulate matter, in this case from a particular satellite called MODIS. And this is an example of the image. You can see where we are about there somewhere. And this is basically just a large array. It's a large two-dimensional array that gives you a value for each pixel, which is the air pollution over that area. Now, rather than just having one of these, like this map, I had thousands of these. I had many decades of daily data. And I wanted to do some what you would think is fairly simple analysis. Things like seasonal means and standard deviations, getting a long time series over somewhere like Cardiff, looking through all of the images, getting individual images at specific times, that kind of stuff. Doesn't sound too difficult. But remember, I've got loads and loads of images. Now, the supposedly simple solution is just stick it all in NumPy. So you use some library or other to load in this geographic data from the satellite. So it could be something like GDAL, or raster.io is a nicer, more Pythonic library for loading in geographic raster data. Store it in a large 3D NumPy array. So you've got one dimension for X and Y, and then you just stack up your images over time in your third dimension. And then you just use NumPy's indexing and slicing and dicing functions to chop and change the array and get the bits you want. But that's actually harder than it sounds, because you need to keep track of everything, which dimension is which, whether is the fifth entry in your time dimension the 5th of January or the 5th of March or the 17th of May, which year, how do you deal with leap years and time zones and all this sort of stuff when you're trying to deal with doing seasonal averages and things. It gets quite difficult. XArray, I think, provides the answer, and it provides the sort of things you can do in pandas for CSV style data, your data frame style things, for large multidimensional arrays. So, XArray, import XArray as XR. That tends to be the fairly conventional way of importing it. And I'm going to give you a few very simple examples of how I can do some of these things I wanted to do in XArray before I then move to talking a bit more about how XArray works and how you can fiddle around with it. So let's for the moment not worry about how we get our data into XArray, but say that we've just got a file here, a netcdf file, this turns out to be, which has got our data in it. If we open it as an XArray data array, we see it's got a shape like a NumPy array. You can see you've got 3 dimensions with a different length for each dimension. But it also knows what these dimensions are called, which is quite handy. And that allows you to do things like this. Here we're taking the XArray array, we're grouping by the season, so the season being sort of winter, spring, summer, etc., and then taking an average over the time dimension. And with a little bit of extra code for plotting this, you get some nice plots like this. So you can see on the left the winter, in the middle summer, on the right March, and you can see you get some slightly different patterns in air pollution over the UK in those times. You can see just about here, and possibly not so well on the projector, you can just about see the outlines of the UK and Ireland, or the west of the UK and Ireland on there. If we want to get a particular location from our array, we can use the isol function. We give it an x and y location, convert it to a pandas data frame, drop the missing data, and bang, there's our time series. Nice and easy. And if you want to get a particular image, we can say, here's an image. If we want to get an image in a particular date in 2014, and bang, there's our image. In this case, with a lot of missing data, unfortunately, because the air pollution measurements from satellites don't work very well when there's cloud in the way. In fact, they don't work at all when there's cloud in the way. So those 3 single lines of code do things that actually take quite a lot of effort to do if you're doing them with pure numpy and fiddling around with trying to keep track of everything all the time. So now I've done that sort of motivating example of why you can do cool things in just a few lines, let's have a little think about what XArray is. Well, XArray provides the data array class, which is basically a fancy labeled version of your standard numpy array. You also have an XArray dataset, which is basically a load of data arrays that share some of the same dimensions. So for example, you could have a data set that had X and Y dimensions fixed and time, and then you've got multiple data arrays with different data, temperature and wind speed and precipitation all over time on the same sort of grids. For those of you who know about such things, a data set is basically a netcdf file stored in memory in Python. It supports all the stuff that netcdf files do. So let's have a little look at how we can play around with a bit of simple XArray stuff. Here's a standard random numpy array with 3 dimensions. If we just pass that array to the XArray data array constructor and look at what we get as an output, you can see that we get the array in the middle, and we've got the 3 dimensions listed here. They each have a length, but they've got no names, and then at the bottom it says, you may or may not be able to see, dimensions without coordinates, and lists those 3 dimensions. So that doesn't really give us anything more than a standard numpy array. But if we start giving XArray some metadata about our array and what it means, it can start to do more powerful things for us. So here we're giving it the same array, but we're telling it the dimensions are x, y, and time. And so you can see it then keeps track of this, x, y, and time, and it knows how long each of those dimensions are. That's the kind of thing that even with just that bit of metadata allows you to say mean over time rather than a mean with axis equals 2 or something that makes no real sense. But also, it still says these are dimensions without coordinates. So we can pass in some coordinates. Here we just pass a dictionary. We've got some coordinates of just integers here. You can do floating point coordinates. And then here, in fact, we've got coordinates that are datetime instances for doing time and allowing us to do some more complicated things with time. And then if you look at your data array, you see this is fully populated. It lists all the coordinates at the bottom. It lists the contents of the array, the length of the dimensions. It knows all about this array, so it can help you do things easily. So what sort of things can you do? Well, firstly, you can select using these indexes, using these coordinates. So here we're saying, let's select a specific time. So in the output, the time dimension has vanished because we've just selected one time, and it lists at the bottom which time it is. But you can see without a little star by it, that means it's kind of an active varying coordinate. And you can see you get a 3x4 array back because you've just selected one of your time slices. You could also use the iCell function, which is the index selection, and that lets you select, in this case, the second time. It's zero-based indexing as normal. And again, you can see you get one particular timeout and a simple 3x4 array. You can do things like slices, so select everything from 0 to 20. You can see you get a couple of x bits out and all the rest of the y's and times there. And it's all fairly simple like that. You can then start applying arithmetic operators and reduction operators across this array. And this is one of the things that's a really simple but effective selling point of XArrays. You don't have to fiddle around with axis equals 1, axis equals 0, which axis am I working on, I've forgotten, and it gets all kind of difficult. You can just say, take a mean over time, nice and simple, nice and clear code. You could take a mean over multiple dimensions at once. So here we're doing x and y, so we just get an average across the whole image for each time step, and you see we get 2 values out, 1 for each of these time steps. I'm using mean as an example here, but you can of course also do median and standard deviation and min and max and all these other sort of reduction arithmetic operators that you can use. And then you can do complicated things. So you can say, you can chain it all together and say, I want to select just data that's in 2014. I want to group it by the month, and I want to take a standard deviation over time. And then if you look at the coordinates, you've got a load of x and y coordinates, and at the bottom you've got a month coordinate. You might be seeing down here with this 1, 2, 3, 4, 5, 6 for the different months it's selected out. There are only 6 months of data in this data set, hence why it doesn't go up to 12. The other thing you can do with XArray that makes it quite powerful for processing large volumes of data, as I said to begin with, I had multiple decades of satellite data that I wanted to process, is it can use a module called Dask. Now, who here has heard of Dask? Okay, so a number, but not that many. So Dask is a module that basically, rather than actually doing stuff on your arrays or your data frames or whatever, it creates a computational graph saying what needs to be done and what depends on what. And then it sort of reshuffles that graph and tries to execute it as efficiently as possible. And this means it only loads data it needs to load into memory, and it only processes things once if you've got intermediate results that are used by multiple different parts of your analysis code. So it's best to explain this with an example, really. In XArray, you can open what's called a multi-file dataset with this open mf dataset function. And here we're opening two datasets, two netcdf files, and we're splitting by chunks. We're chunking it so into lots of little chunks that can be processed independently, and we're splitting it into chunks of 10 time steps at a time. So 10, next 10, next 10, next 10 after that. And then we're simply taking the average over time. Now we can actually look at what the execution graph is in Dask. Now I don't need you to be able to read any of this, it's just the structure that's important. Basically the things in rectangles are data, and the things in circles are functions. And so here we can see we're taking our two files at the bottom, we're getting bits of data from them, they're going up. Here we're doing the mean of each chunk of the files. We've got two chunks here and we're doing the mean of each chunk, and then we're aggregating those means together to create an overall mean. The important thing here is that this processing chain and this processing chain are entirely independent until you get to the final step where you aggregate them together. That means they could be run on separate computers, on separate cores in a computer, in all sorts of ways that can run them efficiently in parallel. Whoops. Hang on. If you do something a bit more complicated, for example, this one, we're taking a group by season and we're taking the average over time. We can see that you get a far more complicated looking graph. This complicated looking graph basically behaves in the same way though. You've got lots of separate processing chains that can be run independently and that share data that's been loaded. So it's been loaded once here and then shared off across these separate processing chains. Admittedly here with a bit of interaction between the chains, so you've got to be a bit careful with that. But again, these can be run in separate cores, separate computers to make it run as efficiently as possible. With Dask distributed is the way that you can run these things on multiple computers. And this is an example of the dashboard that you get access to when you're doing this. All of these coloured bits here are different tasks that are being run, and white gaps are where that particular computer isn't running anything. And you can see that they're being used quite efficiently. They're running things most of the time because it's managed to put this into an efficient graph that shares things and has as much parallelization as possible to allow it to run as efficiently as possible. For those who haven't heard of Dask before, Dask is not specifically related to XArray. You can use Dask arrays without using XArray. You can use Dask data frames instead of pandas data frames. It's a very, very powerful project, very heavily developed. I strongly suggest you check it out. But it is built into XArray and linked very closely, so you can use it very easily with your XArray arrays. So, how do you get data into XArray? Well, it can read certain formats directly. I've already talked about netcdf and how an XArray dataset is basically a netcdf file in memory. It can read HDF, GRIB, various things like that. From my perspective, I want to get in geographic data, geographic satellite data of air pollution. And XArray can now use the raster.io module to read loads of different geographic raster formats. And it's as simple as just using the open raster.io function with a satellite image. And you can see that you've got a load of values. The coordinates are quite interesting. You've got a coordinate for band. These are the different colours, as it were, that the satellite is measuring. So here, often in a standard digital photo, you have red, green, blue. Satellites often have more bands than that because they're looking at different wavelengths. You've then got the Y and X coordinates. Now, these are automatically created from the geographic referencing of the file. So in this case, this file has some metadata attached to it that says this is where the file is located on the Earth, this is how big each pixel is, and so on. And that is picked up by XArray and put into the coordinates. So these numbers here are actually Ordnance Survey grid coordinates, Ordnance Survey eastings and northings, that locate each individual pixel exactly on the Earth. And then we've also got these attributes at the bottom. XArrays arrays can have any sort of attributes you want. You just stick them in there as a dictionary, basically, and these can be passed through all of your operations, so you have information about your array. In this case, we've got the geotransform that allows us to work out where it's located, the coordinate system it's using, the resolution, that kind of thing. So for example, taking my use case of having thousands of satellite image files that you want to combine into a big multidimensional XArray, just take them and stick them into an array with a time dimension. It's basically as simple as that. You can write a little function that opens the file, does a bit of processing on the file name to work out what time the file was taken, what date the satellite image was from, because that's in the file name, and returns a data array. And then you basically just use a little list comprehension to run that function for every file in your directory, and then use the XArray concat function to concatenate these over time, and you get your nice big multidimensional XArray. Simple as that. And if you look at the combined one, you'll see you've got 3 dimensions, you've got your x and y, plus in this case 10 time steps, and you've got all the coordinates there, including the time at the bottom that gives you the information on the time for each of your array slices. Getting raster data out of XArray in a geographic format that can be used by things like GIS systems and provided to other satellite imaging people that I work with is a bit trickier. That's not built into XArray, but I've written my own little library that does that, called XArray to raster IO, and you basically just do some processing in XArray and then use the XArray to raster IO function and give it a file name to save to, and it does it all transparently using those attributes that are attached to the array that give things like the geographic information. So that's my very whistle-stop tour of stuff you can do with XArray, stuff I've done with it with my satellite imaging work. A few tasters of other things that I haven't got time to go into in depth, but that are quite cool that you can do. You can do things like interpolation. So here I'm saying interpolated at a particular X and Y location. Now that happens to be the Ordnance Survey coordinates for here, Cardiff City Hall, and I'm taking that, converting the result to a pandas data frame, dropping missing data, and looking at the first few rows, and this was air pollution over this site in, whenever it was, 2014. That's interpolating it, I think by default, with some sort of bicubic interpolator from surrounding pixels. If I wanted to just get the closest pixel to Cardiff City Hall, I can do the same thing, but saying that I want to use the nearest neighbour interpolation and just take the nearest pixel. And this all works because the coordinates for pixels in XArray are actually given us the centre of each pixel, so you can do that quite easily. You can resample time series, so I've talked before about grouping by a month. That gives you a kind of climatology. What are things like on average in Januaries? So January 2010, 2011, 2012, 2013, all kind of aggregated together. If you're looking over time, you might just want to get an average for January 2010, February 2010, March 2010, and so on. So you just resample in exactly the same way that you would in pandas. It uses the same code behind the scenes. So 1M here just means resample to a single monthly time step. And again, we're taking averages over time. You can do things like rolling windows, again, like you can in pandas. So this is a rolling window over time. A lot of missing data there, don't worry about that. The actual data is hidden in the bits that are replaced by dots. One quite cool thing you can do with XArray is something called OpenDAP, which basically allows you to access large volumes of data over the internet, but only download the bits you need. So this open dataset call at the beginning is opening a netcdf file over an HTTP connection. Now you would assume this would say, download the whole netcdf file, stick it in a temporary directory, open it up, and use it. It doesn't, because there's some special software running on the server. It just grabs the metadata to begin with. And this is a data set, so it has multiple data arrays within it, and we're selecting the TG one, which it helpfully tells us in the attributes is the mean temperature. So this is a climatic data set from the Netherlands Meteorological Institute. Mean temperature data here, you've got all your coordinates, you can then say, okay, select a specific time. So here we're selecting a date in 2009 and plot it. Now, the only data that has been downloaded from that website is the data for that plot. You haven't downloaded all the data from 2008, 2010, anything like that. You've just got the data you need, which is really efficient. And there's a load of XArray extensions you can use. You can do simulation models entirely within XArray. So there's a module that allows you to do things like cellular automata and so on, all working within an XArray array. There's weather forecasting model functions for dealing with outputs of climate models and weather models. One that I found quite useful was an empirical orthogonal functions extension. Empirical orthogonal functions are a bit like principal component analysis, but taking into account space and time in a bit of a complicated way. I'm not a huge expert in them, but it's very easy to do them in XArray. I've got resampled this to a monthly time step, and I just a couple of simple lines of code using the EOF extension, and I get something like this, which looks fairly reasonable if you know a little bit about things like principal components analysis. You can see as you get down to the lower components, you get a lot of noise, but at the beginning you see some interesting patterns about high levels over land and low over sea, and some other sort of patterns there, maybe a pattern here about pollution in the kind of southwest quadrant of the UK, possibly caused by wind patterns and so on. So there's some quite interesting stuff you can do really quite simply. So that was my very whistle-stop tour of XArray. It's a great module, it's an underknown module, but can be really powerful. So go and check it out. Here are some resources, my slides are online, my code's all online, this is all an IPython notebook, and the XArray documentation is very comprehensive and updated very regularly. So thank you very much.
Thank you very much. Any question for Robin? Yes?
Hi, Robin. Thanks for a nice talk. I am a climate scientist. I am using global atmospheric model output evaluation. So I have 4 dimensions. So latitude, longitude, altitude, and time, decadal time. So is it helpful to analyze that data set?
Yeah, so you can do that in XArray. You can have however many dimensions you want. It will store your multidimensional arrays. It will allow you easily to select different times, average over heights, average whatever you want to do. It should work really well for that.
Other questions? Yeah.
Thank you for the great talk. I found it really interesting. I've been through the same process with Tropomi data, so it's almost exactly the same as what you're doing with XArrays. I was wondering, how much data do you have to see a benefit from using Dask? Because I didn't use that for mine.
I'm not entirely sure, to be honest. Partly, I guess I used it because I could, but also because I wanted to get things. I had a computer with admittedly a fair amount of RAM, but not a huge amount, and I was dealing with multiple decades of data. It wouldn't all fit in RAM at once because I was dealing with very large areas. So Dask was very useful there because it was making sure that it was efficiently reading from disk only the bits it needed for that particular calculation. I in fact wasn't using Dask across a cluster. I was using it just locally, so it was running on multiple cores of my machine, but it was still doing all its efficient handling of data and memory usage, which was really helpful to me. So I think when you start getting to the RAM limits of your computer and you can't store what you want to store in RAM at once, using Dask is probably a great first step because it's so easy in XArray. It's about 1 or 2 extra lines of code, and you can play with it. And if you need to, you can then go to some sort of more advanced parallel computing framework if that doesn't work.
Any last question? Yep. Let's thank Robin one more time.